All right, got a few questions this morning for organic, and I'm going to actually answer the homework question first, just because it's pretty quick and easy. And then I kind of got like general questions about cycloalkanes. So, in terms of the general question, problem 15 was what was asked for on the homework. Make sure. Oh no, 17. Hybridization of nitrogen carbon with two structures. Oh, this is the obnoxious one that I disagree with. And it was supposed to be removed, but wasn't. So in terms of that one, it says, I think it's sp3 hybridized, it's sp2 hybridized nitrogen in the first one, and no, it's definitely sp2 hybridized in the second one. I think it's also claiming it's sp2 hybridized in the first one as well. And then carbon is definitely sp2 hybridized in both. So I really hate that question because it's wrong about the hybridization of nitrogen, but if you're curious, the answer to part 1 is nitrogen is sp2 hybridized in both A and B, and carbon is sp2 hybridized in both A and B. So the next question, formamide is planar or nearly so, which structure form best fits that fact? So we've got resonance back and forth too. So if it's nearly planar, this means that so if you look at this, we actually have 4 groups hanging off this nitrogen. So we got nitrogen with a carbon coming out. We're going to have a hydrogen going down, and then we're going to have a lone pair sticking out. So this nitrogen here is actually tetrahedral because of those lone pairs. That lone pair is going to act like a group pushing off. So if it says the formamide is planar or nearly so, we can't be dealing with this structure because the nitrogen here is tetrahedral. This, however, is very planar. So it is very much as written. So the second structure, the one with the nitrogen, the +2, that's the more consistent structure. All right. So the bigger question I got asked was about cyclohexanes, and cyclohexanes are going to be the hardest part of alkanes beyond the naming. So the thing about this with cyclohexane to remember is that there are shorthands that we're using, and the biggest shorthand we're going to use with drawing alkanes is this line bond drawing. And this is how we draw cyclohexane. The problem is that's not what it looks like. But this is a lot easier than drawing what it looks like, because what it looks like is this. So what we had with cyclohexane, and I'm going to regret doing this, but I have to do it. Get the model out. So this top drawing here, it would be considered planar cyclohexane. So what we draw is the planar conformation, and it's the highest energy conformation, and it looks just like that. It's a flat plane. But this, if you take your modeling kit and you build this, you're going to find that it doesn't look like this when you build it. You actually take it and press it down against the table to make it look like this. So what does it look like? Well, we take top carbon, pop it out at us, take the bottom part carbon, pull it back. And so that's what I've got drawn here. And if we take a look at it, this is what's called the chair conformation. So it's called a chair because it look like it. There we go. There's the head of the chair, there's the foot of the chair, and there's the 2 arms of the chair. So this is why we call it the chair conformation. So this is really hard to draw, so we draw it planar even though it's not really planar. So when we look at the actual cyclohexane, we end up, because of how this molecule actually bends, because that top carbon's up and the bottom carbon's down, we actually create two types of groups around the ring. So the first group is called the axial, and it gets this name because of the fact that even in the planar, we've kind of got this Z rotational axis. So we can take the ring and we can spin it around like a top. And when we do that, we're going to get hydrogens, we'll say hydrogens, we're going to get groups that point along the direction of the rotation of this ring. Come on. This kit's a little old, so it's actually quite flexible now. So these are the axial positions within the ring, and you can tell they're axial because if you put them on a flat surface, they touch the flat surface. And if I flip it over, I'm gonna have three that touch the surface. So they'll all stand up on these. Our axial positions point up and down, and if we were to spin the ring, we'd have that z-axis in the center. So these are all parallel to the z-axis. The other groups we get are the equatorial positions, and the equatorial positions are on the equator. So they're basically groups that point away from the ring. And I can designate them with blue, or I will designate them with blue. Now, if I put this model in my hand, the blue atoms don't touch my hand. They point away from the ring and they kind of go up and down. They do zigzag back and forth, and actually if you do the Newman projection, they're gauche to each other, but they point away from the ring. Now, this is a static model that I built. The reality is that I can take, because of conformation, because of how easy it is, because of these carbon-carbon single bonds, I can take one group and flip it around. And when I flip it, now all my blue atoms sit on my hand, so they end up being the axials, and the ones around the white ones that were axial before become equatorial. So what happens with cyclohexane is we have axial and equatorial positions, but they can interconvert. So just because of ring flipping, we can take all the axial ones and make them equatorial and vice versa. So we can't look at a line bond drawing and say, oh, that's an axial atom and that's an equatorial atom, because I can take the model and I can bend it and I can switch them between axial and equatorial. So we kind of have to use guidelines to determine what's axial and equatorial. And the big thing is that bulky groups like to be equatorial. So that's the first thing. If we have bulky groups, they would rather sit in the equatorial position, but we're not going to be able to draw that here because, again, this is drawing it like the molecule is planar. So it's shaped like that. So anything that is cis with respect to another group, if we were to lay these down, we were actually to build this molecule as drawn, they would all be on the same side of the ring. But what we can say is whether or not they're axial or equatorial relative to each other. So what I'm going to do is I'm going to swap out a few of these atoms with red. Actually, no. Let me keep the blue ones. So let's say I take this molecule I built up here with the 3 cis groups. Oops. So this is what I have drawn up on the board. I've got 3 cis groups sitting on the plane of the ring. And now what I'm going to do is I'm going to take them and I'm going to pop them. I'm going to bend this into the chair conformation. There we go. And when I bend it into the chair conformation, what happens is these 2 that are cis are still on the same side of the ring. They are both axial, and the other one, this one, is equatorial. So as I bent it, this is axial, equatorial, axial. But I can get ring flipping. And because of the ring flipping, I can take all the axials and flip them equatorial and all the equatorials and flip them axial. So I can also take this ring and I can bend it. And I can get these 2 equatorial and this one axial. But the thing is, I can never bend this ring in such a way that all 3 are axial or all 3 are equatorial. We're always going to have this stagger of axial, equatorial, axial if they're cis to each other. If they're trans, so if I draw this, So if I start out with them trans and then I start bending this ring, what I get is that all three are equatorial, or if I do ring flipping, they end up being axial. So in this case, they're either all three going to be axial, or they're all going to three be equatorial. So the only thing we can say from the line bond drawing is relative to each other, are they in the same positions or are they in opposite positions? And there, if you go through the notes, there's actually like a few different ways you can do this. You can memorize it, you can build the model. I would recommend building the model because the memorization is a bit more complicated. But if you're just the type of person that wants to memorize a bunch of rules, if we number these carbons 1, 2, 3, 4 around the ring. And we're going to talk about them relative to the first position. First question you need to ask is, are they in position 2 or 4 or position 3? So if they're in positions 2 or 4, next question, are they cis or trans? And this is all going to be relative to the first carbon. Well, if they're in position 2 or 4 relative to the first group, and they are cis, they're always going to be opposite. So if this is axial, this is equatorial. If this is axial, so we have this. If this is axial, this will be equatorial. Or if this is equatorial, this will be axial. If this is equatorial, this will be axial. If they're trans, they're on the same side, in the sense that they will both be axial or both be equatorial. Now, in this case, for the second position, it'll be axial but opposite sides. For the fourth position, it'll be axial but the same side. So, again, relative to group 1, if they're in the second or fourth positions, if they're cis, they're going to be on opposite sides. If they're trans, they're going to be on the same side. It's flipped for the third position. So the third position, if they're cis, they're on the same side. And if they're on trans, they're opposite. So again, what we mean by the same, if this is axial and this is cis, this is also axial. If they're trans, if this is axial, this is equatorial. So that's how they are relative to each other. Now, as far as which particular group prefers axial or equatorial, this is purely bulk. So what we want to do is maximize the number of bulky groups that are in the equatorial positions, because those actually get further away from each other. Our axial groups here will push on each other, so you can kind of see it here on the top. But if we make them equatorial, they all flare away from each other. They all move away. So what we want to do is maximize the number of groups that are in the equatorial positions, particularly bulky groups. Now, if we have a situation where they're on opposite sides, so let's say we've got, we'll keep it easy. So we'll go to first and second. And since these are 2, 4, and they're both cis, they're on opposite sides, whatever this group is here, we're not going to be able, well, since they're both methyl groups here, we're not going to be able to find a more stable conformation. They're just both, one's going to be axial and one's going to be equatorial. So if I build that, so this is my cis 1, 2. There is no way to get them both equatorial. So if I make one axial, one's going to be equatorial, vice versa, because if I just ring flip, one's going to be axial, equatorial. But let's say instead of them both being methyl groups, let me make this a tert-butyl group. I'm going to start piling on the carbons here. Well, in this case, If I have this one axial, it's going to be pushing up against all the hydrogens that are here. So if the groups aren't the same, I'm going to maximize the number of bulky groups that are in equatorial positions. So, come on, there we go. So what I would do is I would say that this tert-butyl group here is definitely equatorial. And then use this flow diagram to say, well, it's one away from it, and we want them on opposite sides. So this one's going to end up being axial just because it puts a smaller bulky group into the axial positions. But again, we don't know that looking at this drawing. And the reason we don't know it looking at this drawing is that this drawing is not representative of what's really going on. This drawing makes it look like these three groups, these two groups on the ring, are in a planar ring, and this is how they look, and it's not what's going on. What's going on here is that we have a chair conformation with axial and equatorial positions. So we're going to actually take outside information to determine which groups are axial and equatorial. And I think especially for the discussion boards here, like several of them are just methyl groups. So you're just looking at the methyl groups relative to each other. The only thing you're going to be able to say about the methyl groups is what are they relative to one another. So again, as drawn, there are no axial and equatorial positions in this drawing because this is a planar ring. But what we can say is that if they're both cis and they're sitting in a 1-2 position, they're going to be on opposite sides. One's going to be axial and one's going to be equatorial, but we don't know which one because the ring can flip around. The only thing we can say is that relative to each other, they're going to take opposite positions. But if we have where they're like 1-3, cis 1-3, they're on the same side, so what we can say is they're both axial and both equatorial. And particularly because these are methyl groups, they're probably going to both be sitting in equatorial positions because that's the more stable conformation. But we can definitely get them to flip axial every now and then. So that's kind of like the axial equatorial in a nutshell. Again, this can't tell you axial and equatorial because this doesn't have axial equatorial positions. It has positions above the ring and below the ring, but not sitting like equatorial axial relative to the ring. Because the real drawing of this structure is this. And we've got one carbon up, one carbon down to give us this chair conformation, and those can flip. And because they can flip, just because something is axial in one drawing, we can flip it to be equatorial in another. So that was it for the questions I got asked in advance. Let me check my email just to make sure that statement's correct. So yeah, just number 17 on the homework. Cyclohexanes and axial and equatorial. All right, so I've got 0 concurrent viewers. So what I'm going to do, just going to turn the camera off. Again, these are not lessons, they're not lectures. These are office hours, but I do have the chat menu open. So if you do have questions, type something in chat. There's about a 1-minute lag on this video. So when you type, it takes me about a minute to get to it, minute to see it. But I'll answer your questions as I see them. All right, so that's the end of the office hours. Again, if you have questions, please feel free to email them and I'll answer them at the start.